Temperature, that was for the synthesis of ammonia, correct? The value of K for synthesis. That's what we did. Now, would somebody tell me what the value of K was again for synthesis of ammonia?
3.84 times 10 to the fourth.
Times 10 to the what?
Fourth.
Negative fourth or fourth?
Fourth.
Fourth. All right, now, how's this chemical equation different than it was from A?
It has more things on the product side.
Right, so we had synthesis before. What is this one called?
Decomposition.
Decomp. Good. This is a decomposition reaction. So now I'm asking you to solve for K of decomposition. We know it's what over what, Caleb? Yes, you do. K is always what over what? See, you do remember, yes. So products over reactants. So go ahead and calculate the value of K. 10 points if you can do it faster than I can. I'm done.
1 second.
What'd you get? Tell me what you got.
I don't think I did it right.
I know. What'd you get?
6.9 times 10 or so.
Nope.
I know.
Patricia? Times 10 to the what? Yeah. But you guys, didn't you flip this as compared to the previous one? Didn't the reactants and products flipped?
Yeah, I realized.
Oh, so couldn't you have just taken K of decomposition is equal to 1 over K synthesis? Because put in your calculators 1 over 3.84 times 10 to the fourth and tell me what you get.
Probably 2.6.
Oh, you mean this?
Yes.
Yeah, you do.
I just wanted to write it all out.
That's why I did it so quickly.
Yeah, I realized that half by when I was writing it. I was like, wait, I'm doing things.
Summer, did you find your error? Sorry,
I think
Morgan.
I just calculated.
Calculator error. All right. Is everybody good with this? All right, now try this one. So calculate the equilibrium constant for this reaction. Was that 3.84 times 10 to the fourth? Was that our original?
Yeah.
Thank you. So yeah, I got 190. Now, would you guys do me a favor? Would you take the square root of this number, K prime, please? Take the square root of that.
It's going to be that answer.
It is going to be that answer. 195? Okay, she had 194.8. Okay. It is 195.
Yes.
Okay. And the square root. Now, see, didn't we cut the concentrations in half from the first? Yeah. Shouldn't this be 1/2 here, guys?
Where?
Shouldn't this be a 1/2?
No, you didn't.
No?
You didn't have it.
Okay, that's fine. But didn't we cut the concentration of everything by 1/2 here? Yes?
Yes.
All right, so then if we cut this by 1/2, then we end up taking the square root of the K value.
This class is really tired, really messes
Oh yeah, now here's the conclusions about the equilibrium expression. These are the things that that problem was designed to illustrate, to show you. Number one, did I write all this down on your paper? Oh, then you better write it down. I didn't write down this.
So why wasn't the intended equation?
Okay, yes, I put it in words, I didn't put it in math. So I just want you to write this math down. So K forward is equal to the reciprocal of K reverse. So if on one side it's a synthesis and then the other way it's a decomp, they're reciprocals. The value of K is the reciprocal of each other. If you multiply the equation by some number,
What is that, K1 or K5?
K prime. So if I multiply the original equation, in the last problem, we multiplied the original equation by 1/2. So that meant K was raised to the 1/2 power. And we know that if you raise it to the 1/2 power, that's really the same thing as the square root. And no units for K, no units for K. Yay, hooray, yay, hooray. No units for K. Capiche?
Yes.
Abate. K does not care about temperature. The equilibrium expression does not care about temperature. K does not care about the amounts either.
What do you have right now in class?
K at temperature 1 is equal to K at temperature 2.
I'm sorry.
That's okay. It's hard to read. I'm sorry. Thank you for asking. You want me to write it?
That's fine, I got it, unless someone else needs it.
Well, I'll do it, yeah, in case somebody else needs it. K at temperature 1 is equal to K at temperature 2. When I say there's many equilibrium positions, I mean, we could sit, depending on where you have it, favoring reactants or favoring products. That's fine. But the value of K does not change because it's always going to be products over reactants. It is a ratio. If this number, if we add to the products, the reactants will shift to keep K the same. If we add to the reactants, the reaction will shift to keep K the same.
Why does it do that?
It's called Le Chatelier's principle, and we'll get there. If the reactants get big, what happens to products? It gets bigger too. If reactants get small, what happens to products? It gets smaller also. Nice PowerPointing, eh?
Impressed by the answer.
Alrighty. Pressure is directly proportional to concentration. And we can treat equilibrium pressures just like we treat equilibrium concentrations. Yay! Now, most of the time when you see the big K, it means K sub C. What does the C mean? Concentration. So when you see just the big K, we're talking about concentrations. But we'll use K sub P to refer to pressures. But they behave in exactly the same way. So if you're dealing with something that's all in gases, they have pressures, not concentrations, but we're going to treat it as if it were concentrations. It behaves the same way. So take a look at this problem, and I'm going to ask you to calculate K sub P in the exact same way you just did before, but now use pressures instead of concentrations. Go. What'd you get, Summer?
No,
She doesn't calculate, she's asking me to set up.
Oh, no.
Yeah.
All right, what'd you get, Pashad? 3.87? I went with 3.9 for sig figs. Go on. Times 10 to the what?
4.
That's what I got. And my unit?
You guys can burn this.
No.
There's no unit. Good. Questions about that?
My scientific notation took me to 1.59.
Yeah, that's a problem.
Yeah, I don't know what's going on with that.
We'll have to take a look at your calculator usage, okay?
Okay.
Okay. Any other questions about the setup? Joey, you good? All right. Kaizen, you good?
1.59
Good.
to
But your setup's right, Morgan, right?
Yeah.
All right. So it's just calculator usage at that point.
Yeah, like, it's just like I got the question and I was just gonna put it inside specific notation setting just to make.
Now, there is a relationship you can get from pressures to concentration using this handy-dandy equation. I'm not going to require that you memorize the equation. No, I almost never use it. Delta N is the sum of the coefficients of the gaseous products minus reactants. Again, P minus R, it's alphabetical. This is all on your papers, yes? All right. R is the ideal gas law constant, R. Notice we're not dealing with energy here. That I won't give you. I will not tell you the value of R to use. But I always found it pretty easy to remember because, look, pervnert, PV equals what? And don't you just see the nRT right there? I can see the nRT, so I always knew this was the ideal gas law R because I could see the nRT and there aren't any units here dealing with energy. And K doesn't have units. So that's why I knew it was the ideal gas law R, not the energy R. Temperature, of course, has to be in Kelvin. What else is new, right? All right, so using the value of Kp from our previous example, and what was the value of Kp? Somebody tell me, please. Kp was what? 3.9 times 10 to the... Calculate the value of K at 35 degrees Celsius. So this is asking you to use that equation we just used. So, would somebody read the equation for me? K equals... Somebody read the equation for me? K sub P equals... There we go. So I'm going to rearrange this because I prefer to do that. So K then is going to equal, Kp divided by RT raised to the delta N. So K is going to equal 3.9 times 10 to the 4th divided by 0.08206 times, let's see, 35 plus 273, somebody.
Really?
Thank you. Raised to. Now, the delta n is the sum of the what?
Coefficients.
Products minus
Unreacted.
reactants. So that'd be 2 minus 4. So that's to the negative 2. All right. Yep, 2.5 times 10 to the 7th. And the units on K, please? There aren't any, yeah.
Did you get that one?
Everybody good with that number? Blaze? You sure? Or are you just saying that? Oh, I was talking to Blaze. I know you did. Blaze, you just saying that? Did you really get it?
Yeah, I'm not sure.
Okay.
Is this the whole packet?
No. Nice try. Yeah, right. Okay, homogeneous equilibria. What's the prefix homo mean?
Same.
So this just means everything's in the exact same phase. In this case, it's all gases. And there's a reason we need to know this, and you'll like the reason. Trust me. Here, all the same phase. They're all aqueous. I know, I couldn't resist a Schrodinger's cat picture. I couldn't resist. Heterogeneous means more than one phase. Like this, you got liquids and gases. Hetero is more than one. Hetero means different. Hetero means different. So here's different phases, liquid, gas, gas. Or here we have solid, solid, gas. The equilibrium position does not care about solids or liquids.
Why?
Because solids and liquids are, kind of think of it as once they're made, they ain't going back. So the good news for that means we get to ignore them because their concentrations, their values become constant. We don't have concentration values for solids, do we? We can do grammages, but we don't do concentrations. And so we can assume that its value is insignificant. And because we can assume it's insignificant, we get to ignore the solids.
Yes.
You get to ignore the solids. Therefore, solids never appear in an equilibrium expression. Solids never appear. Solids never, ever appear in the equilibrium expression. Solids never appear in the equilibrium expression. So what would the equilibrium expression be for this particular problem?
Yes.
K would equal what? K is going to equal what? Not 302. Not 302, no. You're on the right track, Morgan. It is the O2. But not 302. What do we do with these coefficients? There you go. Like that. Cube it. Oh, look, there it is. That's why I was saying not 302. Do you see now, Morgan?
Yeah.
Summer question? Oh, sorry. There's some mints on my desk if you want. All right. And guess what? We never, ever, ever put liquids. No liquids. Never put liquids. Never liquids. Never you put liquids in the equilibrium expression either. We don't have concentration values for pure liquids, do we? No, they're pure liquids. They aren't solutions. So we assume it's insignificant and we get to ignore it. So what would the equilibrium expression be for this problem? Morgan, take it away.
H2 squared O2.
And what? O2? Yep. We get to ignore the liquids. Did you? Okay. Yeah. I just want the expressions. I don't want you to solve them. I just want the expressions. Okay, you ready? All right. Is this A on your paper?
Correct.
Okay. So what are you going to need first?
Balanced equilibrium.
Balanced chemical equation, yeah. Oh, it's balanced. So what is your equilibrium expression for this?
K equals CO2.
K is going to equal Cl2.
Oh, concentration of CO2.
Well, actually, no, because it's a gas. Technically, I would write K sub P is equal to the pressure of the Cl2.
Do you still put it in brackets?
No, that's only for concentration. But if you had written K equals Cl2 in brackets, I know why you did it. But that's the technical way it should be since we're dealing with pressures.
Okay.
Questions? Okay, try that one.
It's meant to be right.
I have it up here.
It's one.
Mm-hmm. Did you get it? Okay, so why do we need to know an equilibrium constant? Well, number one, you can predict whether or not a reaction will happen. That's a good reason. These are on your papers, right?
No.
Oh, bummer. Do you remember the lab we did in 8th grade with the, in 8th grade, way back in Chapter 8 in Gen Chem with the unknown solutions that you had to identify?
Yeah.
One of the first times I did that, I followed the instructions given in the lab manual at that time. And the concentrations of the ions was insufficient. You could mix them all day and you wouldn't get product because the equilibrium expression was too far to the reactant side and I wasn't getting enough product. But when I increased the concentrations, I was able to shift the position so that I could actually make product. If you don't have enough ions in the solution, remember collision theory?
Yeah.
If you don't have enough ions in solution to actually find each other, to collide, to make product, then you aren't going to make anything of significance. So whether or not a reaction occurs does, to some extent, rely on how much you have. And that's why the equilibrium expression will allow us to predict whether or not a reaction occurs. It can tell us whether or not we're at the equilibrium position. Or is there more reaction that's going to happen?
Is there any way we can abbreviate equilibrium?
Yeah, I use an EQ for equilibrium. I think I used EQLBM in my notes. A lot of my abbreviations tended to just drop out vowels.
Gotcha. Makes sense.
Mm-hmm. And I can tell which direction it will shift. Is it going to shift towards equilibrium or away from equilibrium? Am I going to shift towards reactants or shift towards products? And as a chemical engineer, that's a huge thing to know, where your equilibrium position lies. Because if you end up with a low yield of product, your boss person is not going to be very happy with you. Nope. Yeah, everything looks great on paper, great thermodynamics, but your yield of product is 2%. What was that? Yes. Or pharmacy. Sometimes when medicines cost like hundreds of thousands of dollars per pill, you could probably guess where the equilibrium expression is going to lie. Thank you. That's probably all I have. Low yield of product. Huge cost because your product yield is so low. Or they're just greedy, one or the other. All right, there's a couple things you need to know about the extent of a reaction. Is any of this on your papers? No. Okay, so R to P, so everybody should know what R to P means. Reactants to products, good. So if K is a very, very big number, see, notice, watch, see, K got really big. If K is a big number, where do you think the equilibrium position is? Summer?
I don't know. Think it
Is the position going to lie at products or reactants if K is big?
okay.
Why would she say products, Morgan?
She would say products because when you're dividing by the reactants, it will be, like if the reactants is smaller and you're dividing, your products is being divided and reactants are smaller, the numbers can be bigger.
Yes. Products is the correct answer. When K is large, it lies towards the products. Because when your numerator,
Oh, it says that right here.
yes. Oh, good, it does say that. What's it say, Patty?
Does a value of K much larger than 1 means that the equilibrium, the reaction system will consist of mostly products, the equilibrium lies to the right.
Yes. So here we end up on the right, high yield of product. When K is much greater than 1, we end up with a high yield of product. Oops. So products. The reaction lies towards the product side. What was that?
The products of the little fat
Yeah. Or the big fat kid.
kid. Okay.
All right. Now, when reactants, well, when K is very small, what's true about this now?
Reactants are much.
Right. And reactants sort of run the show in this case. K is much smaller than 1, and we have a low yield of product. Alrighty. And so our teeter-totter would look like this, showing the big fat kid on the R side of the teeter-totter. Now, what if K was equal to 1? If well, no. Equilibrium positions could be any place, but the balance part would be right. It means your concentration of reactants and products would be equal, right. So if equilibrium lies to the right, the value for K is
Large.
or large. Large works. And if it lies to the left, the value for K is smaller or much less than 1. Either one is fine. Either one would work. It's all good. Oh, look, I got this question there. Based on the picture below, what is the value of K? 1. Yeah, it'd be 1. No, I did not cut and paste that nice little drawing onto your paper. I did. Now we get the Q value. Now the good news with the big Q is it works just like the big K. The big Q is just like the big K. Oh look, I got products over reactants this time. Yay me. And yes, we still get to use the coefficients. But in this case, the difference is initial concentrations. What's K use?
Given concentration.
Not given. Not final. Equilibrium. Right. K uses equilibrium concentrations. Equilibrium concentrations. Q uses initial concentrations. And we can compare K's to Q's to tell the direction that this thing's going to shift. Is it going to shift towards products or is it going to shift towards reactants? But what if we knew K was equal to Q? Then what?
What do you mean?
Well, we're looking at the value of Q. We're going to compare it to K. And because we can compare the two, we can tell if the reaction is going to shift towards reactants or shift towards products. But if K were to equal Q, then what's true? Then we're at equilibrium. Ain't no shifting going to be taking place. So here's a way to look at it. When Q and K are the same, you're at equilibrium. Ain't no shifting going on. But when Q is less than K, when Q is smaller than K, and these you'll have to know to solve some of the next following rest of the chapter problems. You have to understand this relationship.
Okay.
Otherwise you'd be solving problems not correctly. In order to get, because everything wants to be towards what? Equilibrium. Q is less than K. Am I correct in this statement?
Yes.
Yeah, that's a problem. So which direction are we going to shift? Towards reactants or towards products?
Reactants.
Why would I shift towards reactants?
Because products need to be consumed to equal the reactants out, right?
Well, let's think about it. Let's look at these two K's and Q's. In order for, we want them to be equal. That's our end game goal. We need these guys to be equal. How am I going to get these guys to be equal? Who's got to go down? Okay. In order to get this to move towards equilibrium, the shift then has got to be towards reactants, just like you said. So when Q is less than K, the shift is towards reactants. And look at this. Who's he pointing towards? Who's this tip pointing towards? If I were to look at reactants and products, who's this pointing towards? If I say reactants to products, who's that pointing towards? Reactants. Yay. So our shift is towards the reactants. Do you see that? If Q is less than K, our shift is towards reactants. Do you see how it's pointing towards reactants? Do you see that? Do you see that? All right. Now, what about if Q is greater than K? Our shift will now be towards products. And can you see it's actually pointing towards the products? Do you see that? Good. So if you can remember Q and K, and if you think of Q as being reactants and you think of K as being products, do you see that? Look at who it's pointing towards. In this case, it's pointing towards products. So that's the direction of our shift. Got it? Now take a look at this original problem. At equilibrium, the concentration is 4. Do you see that?
Yes.
All right, let's go back to this. At equilibrium, the concentration of this ion is 4. So, if the concentration of this ion at equilibrium is 4, doesn't this become 4? So what does this become? 6. And then what does this become? 2. So now K is going to equal 4 divided by 6 times 2. Going forward to see if I had anything actually PowerPointed up for you, and I don't, and that's okay. So K is equal to 0.33. Now, let's take a look at the icebox. So I like to write it out. So Fe 3 plus the thiocyanide ion negative.
Wait, I thought we were solved for Q in the last one.
Well, we knew Q was 0. I was asking which direction did it shift.
Yeah, sorry.
No, that's okay. That's 3 points. Good question. So I like to write down the equation SCN 2 plus. Okay. Initially, what is my initial conditions for this new reaction?
6.0.
So I have 6 of those, right?
Yeah, of the one makes up for
How much of this do I have initially?
I don't know.
We don't have any.
Oh.
Which direction will this thing shift? Yeah, it'll shift towards products because I don't have any products. So then the question says, how much will I make at equilibrium? So again, I need to know my change. So is this going to be a positive or negative X under the iron? Yeah, it's going to lose some. What about the thiocyanide? It's going to lose some. What about this one? It's going to gain some, isn't it? So down here, I end up with, at equilibrium, my amount of iron will be 6 minus X, correct? At equilibrium, the thiocyanide will be 6 minus X, yeah? And this will be X. We know that K is going to equal products over reactants, yes? So we end up with X divided by 6 minus X squared.
Why'd you s- oh.
So now you just have to solve for X.
Are we using the one that we are using one?
Now, would you like to see how to make your lives easier to solve for X? Great. I need you to turn the lights on, please, and pick up a calculator. Okay, one of the first things you have to know for the equation solver is the equation solver does not like to have a variable in the denominator. And the reason it doesn't like to have it in the denominator is it's going to use alternating increments, your calculator will, to solve for X. And if those alternating increments run through 0, it will freak out because you can't have 0 in the denominator. So the first thing I'm going to do with this equation is I'm going to rewrite it so that I have 0.33 multiplied by 6 minus X squared equals X. That's the first thing I'm going to do. The second thing you need to know about your solver is it's already set equal to 0. So then I need to rearrange this equation so that it's set equal to 0. 33 multiplied 6 minus X squared. Oops.
What was that one doing?
Yeah, having a brain fart. Minus X.
Okay.
Okay, because now it's equal to 0. You good with that? All right, so that's what we want to enter into the calculator. So now you're going to punch in math 0. And it should say at the top, equation solver, equation,
Okay.
semicolon 0 equals. Everybody see that?
Yep.
Now, I like to use parentheses to start with because, you know, sometimes you just can't have enough. 0.33 parentheses, 6 minus X, end parentheses, and then you want to square that guy. And then I'm going to close it off and go, okay, that's everything on that side, minus X. So it should look like this.
Oh, I already pushed enter.
That's okay. Everybody got that?
Wait, can I see again?
Mm-hmm. Everybody good with that? All right, now hit enter. And now yours all says what? X equals 0?
I got X equals 10.
Yeah, it just depends on who. Mine says X equals 255. It doesn't matter. I'm going to go ahead and push 0, but it really doesn't matter. Now, look on the enter key of your calculator. See where the green says the word solve?
Alpha enter.
Well, you see where the green says solve?
Yeah.
And you see the alpha key is green? So you want to hit alpha. Yeah, because you want to hit the solve. So we're going to hit alpha enter. Oh, and it's going to start thinking about it. And then it pops up an answer.
2.98.
Now be careful. Do you see the ellipses at the end of the 2.98? Do you
I
see
got
that?
12.04.
Oh, yeah.
I got error.
Times 10 to the.
Okay. If you got an error, there was a data entry, and I'll go back and look at those. But stop for a second. Stop and pay attention. Stop and look over here, and I'll find out what your error was.
Oh, I got it.
Oh, good. Now see those ellipses at the end?
Yes.
Biggest problem students make is they ignore that could be an issue. Hit second quit for me. Do you see how it says X equals that number?
Yes.
Hit second quit.
Okay.
Push in the letter X that's found underneath the word mode.
X
hit enter.
equals 2.9.
In this case, you're good. A lot of times it'll say 2 point something times 10 to the something.
I got 12.04. There's two
What is the
possible
major, oh, the
roots.
hair. There's a, now, for this equation, how many possible roots were there?
2.
Right, there's 2 possible roots. So Morgan came up with the second root, and that's not a plausible answer because 6 minus 12 would have given us -6. We can't have that value for concentration. So then you solve that by changing your value of x to something different, or you could actually graph it. But if you end up with a root that's like not possible, that's what's happened.
Okay.
Now, one of the really nice parts about that being stored already in for x, you need the concentrations of everything, correct? So if you already have the x value stored into your computer, all you have to do now, take your calculators and type in 6 minus x. And that value is already there for you. So when you're dealing with numbers that are not so nice, like this one, you know, this one happened to have, somebody jacked my charger. So somebody happened to have not.
Courtney Ritchie, come to the office, please. Fine Arts Activity before school, 7:45.